Okay, can you hear me, Bob, now?
Yes, I can.
Awesome. So let's get started. Hello, everyone. Thank you so much for joining me today for our seminar regarding the application of satellite imaging in the oil and gas industry. We have Bob and Gordon here from MDA company. They are experts in this matter about the application of imaging and image analysis. Learning from the images coming from the satellites, very fantastic and interesting technology being used these days in the oil and gas industry. So please join me to welcome Bob and Gordon in our seminar. And thank you so much, Bob and Gordon, for your time. And thank you so much for teaching us about your project that is ongoing in Western Canada. Thank you so much.
Okay, excellent. Thank you. And it's actually our pleasure, Hussein, to be able to speak with your folks at U of A, my alma mater, from a long time ago. So hello to everyone there. I graduated in forestry back in 1978, long time ago when the earth was green. Anyways, thanks a lot for that. I don't know, Gordon, do you want to say a couple words of hello?
I will. Good morning, everybody. My name is Gordon Staples. I'm with MDA based in Vancouver, and I primarily focus on the development of radar applications, but I also work with Bob and the other more business-focused team on developing proposals and solutions to meet our customer needs.
Perfect, thanks. So what we thought we would do is introduce MDA, a very short commercial for you, and then Gordon will take over and do some applications. Well, first of all, the science of radar, and then some applications offshore. And we'll continue with more of the onshore Alberta, onshore global kind of applications that we do with our spaceborne radar. So as a company, MDA is one of the oldest and largest integrated space technology leaders in Canada. So we've participated and developed and created or built over 300 missions, satellite missions. One of the largest imaging missions that we created a long time ago was RADARSat-1. That was one of our first imaging satellite missions, and that actually appeared on the back of the $100 bill in Canada for a number of years. We were on every one of the shuttle missions. So this robotic arm, this Canadarm that you may know about, is an MDA product. We're also providing the robotics to the International Space Station, many other satellite missions, including Japanese and other US and international satellite development missions. And on the missions to Mars, we've had robotics and close range imaging and laser profiling, that kind of technology there as well. What we're going to talk about today is this asset called RADARSat-2, which is collected in addition to RADARSat-1, which was 72 billion square kilometers of imagery, equal to 141 times the surface of the Earth. So that was RADARSat-1, and RADARSat-2 has already collected that much imagery of the Earth. That's what our focus is on today. We're actually set up in 3 different divisions. Gordon and I are in the geointelligence business. There's a robotics and space operations, and there's a satellite systems division at MDA. Again, we're going to look at radar imaging satellites as the key focus. So MDA as a company has been around for 50 years and has participated in, like I said, the Canadarm space robotics programs for 40 years. And we're a global expert in radar satellite imaging with lots of experience in that domain. So as I mentioned, we're going to focus on SAR science first with Gordon, and he'll definitely provide lots of information on our asset that's on orbit now, which you see in the lower right of this slide, called RADARSat-2. He's going to cover offshore energy applications, as well as something that leads us to the new shift in the energy business, which is something called nature-based solutions. And then I'll cover the more traditional pipeline monitoring and oil field and energy infrastructure monitoring at the end of the session. We've got a lot of information, a lot of material here, so I will stop my share now, Gordon, and I'll let you go ahead with your slide deck.
Okay, thank you, Bob. Okay, good morning again. And what I'd like to talk about is SAR concepts and offshore applications. And brief outline, I'll go over as I just mentioned, the SAR concepts. I'll look at three areas for offshore applications, just the general area of oil slick detection, look at oil seeps, and a few comments on the detection of natural gas seeps, and then go on to what's termed to be nature-based solutions. So going now, looking at SAR concepts. So the key thing is what is synthetic aperture radar, SAR? So in general, if you have a regular radar, what's called a real aperture radar, the radar resolution degrades increasing altitude. So for low flying platforms and aircraft, whatever, 10,000 meter altitude, not a big deal. But if you're looking at a satellite with a altitude of about 800 kilometers, that's a huge problem. So if you had a traditional radar, in order to get the resolution, on the order of tens of centimeters to the meter scale, you would need a satellite with an antenna length on the order of 3 to 4 kilometers. So clearly not practical. And this whole idea of what it amounts to synthesizing a long antenna from a short antenna introduces the notion of synthetic aperture radar. So in essence, the resolution benefits of a long antenna is synthesized by a relatively short antenna. So a typical antenna for a spaceborne radar is on the order of 10 to 15 meters. So by using that antenna length and by synthesizing the benefit of a longer antenna, the resolutions in tens of centimeters to meters is possible. So just a brief look at some of the radar set to imaging modes. There are 24 or so imaging modes on the satellite. And the imaging modes of the satellite are characterized by an image size and resolution. I'll get into that in a minute. So for the most part, if you're looking out in this area, these are the wider swath imaging modes. So a typical image there could be on the order of 300 by 300 kilometers, 500 by 500 kilometers. Resolution there is, 50 to 100 meter resolution. And we primarily use those modes for a lot of ice applications and maritime surveillance. And typically for those modes, you don't necessarily need higher resolution. As you move into this range here, the spatial size of the image decreases, but the resolution goes up. And those modes in this area here also include the polarization capability, and I'll talk about that in a minute. So that combination of the higher resolution and the polarization adds significant information to the radar image. And we use those modes for a lot of applications where we're trying to get, classification potential. So crop monitoring, forest classification, etc. And then we move down into this area here, and this is where we go into the higher resolution modes of the satellite. And sort of the price you pay for the higher resolution modes is that you have quite a significant reduction in the spatial extent of the image. So these high resolution modes are used for areas where we want the the most resolution information that we can get over a relatively small area. So, looking at forest change, for example, and when you get into the very high resolution, land intelligence, military applications, mapping, and other applications as well. So what a radar satellite or any satellite does in general is it will start imaging. So for example, with RADARSat 2, we can say start imaging at the equator if we wanted to, and image many, many thousands of kilometers. So we acquire a continuous strip of data. So an example here, this is off Vancouver. So this is just an example of a strip of data. So we can acquire a strip of data. The satellite has a speed of about 7 kilometers a second. So this is on the order of, maybe a minute or so or less to acquire this data. So we acquire the data and then we process that into an image. And as I'm talking going forward on the presentation, I'll refer to an image. And for the most part, the images that once the data are processed and converted into an image, a typical image is typically square, just by convention. So as I was talking about, there's always this trade-off with spatial coverage and resolution. So going out here, this is a ScanSAR Y. This is a single image here, 500 by 500 kilometers, 100-meter resolution. So that particular mode we use very commonly for ice applications. Down here, ScanSAR Narrow, say 300 by 300 kilometer scene size. So going forward, I'll just call it a SWAT with like 300 kilometer SWAT with just to reduce the talking a little bit. So ScanSAR Narrow, 300 kilometer SWAT with 50-meter resolution. We use that a lot for maritime applications. And you can see the pattern here that as the size of the image, the spatial extent gets smaller, we have progressively better resolution. So the highest resolution is called Spotlight, and this is Spotlight buried in there. Relatively small scene size on the order of 18 by 8 kilometers, but resolution on the order of about a meter. One exception to this is a mode that was specifically developed to meet end user needs, and this mode goes by the term of extra fine, and it's 125 kilometer scene size at 5-meter resolution. So it's a pretty good balance of spatial coverage and resolution. So depending on the application that we are doing and our customer needs, we look at the availability. Are they interested in wide area imaging at coarser resolution, something in the middle, or do they want very high resolution over a relatively small area? So looking at the resolution here, so ScanSAR Narrow, 300 kilometer scene size, 50-meter resolution. And we look at an example here. This is a subset of that image, 6 kilometer scene size, 50-meter resolution at Vancouver Airport. So you can look at that and, with a bit, not too much imagination, see it's an airport, but you're not getting a lot of detail. And that makes sense given the 50-meter resolution. As you drop down, so now you go down to another imaging mode. This mode is standard. It's 100 kilometer scene size, 25-meter resolution. And when you get into that imaging mode, again, the Vancouver Airport, and here that higher resolution is bringing you progressively more information. Go down to another imaging mode. This is multi-look fine. So 50 kilometer scene size, 10-meter resolution. And now, because of that increased resolution, you're getting progressively more details about the airport. And there's a number of features there that become very. And finally, drop down to the Spotlight mode. Highest resolution the satellite can do. It's a bit of an imbalance on the resolution here for a number of reasons. Anomaly, but a one meter resolution at a 18 by 8 kilometer scene size. So we look at part of the terminal area of the airport, and you can see the jetways coming through here, some of the ventilation equipment on top of the airport building. So again, gives you extremely good detail, but at that reduced spatial coverage. So transitioning now to look at polarization. And if you're familiar with optical images, the optical images change the frequency. So whether it's in the visible range, the infrared, the shortwave infrared. So the frequency that the data are collected varies a little bit. So you get the information from the surface that you're looking at, the target on the ground. In the case of radar, the radar frequency or the wavelength is constant. But what is done is to vary what's called the polarization state of the radar. And that increases the information content. So for imaging radar, there are two polarization states. There's a horizontal and a vertical. And as the name implies, the horizontal is, for all intents and purposes, parallel to the Earth's surface. And the vertical polarization is vertical to the Earth's surface. So there are two fundamental transmission modes. There's copolarized, so you can transmit horizontal, receive horizontal. That's called HH. You can transmit vertical, receive vertical, VV. And you can also transmit a copolarized. So you transmit the horizontal, receive the vertical, and vice versa. So each one of these polarization states brings slightly different information to the radar image. So looking at that. So single polarized image. So we can acquire that if we want. You select the polarization state, whether it's the copolarized or the cross-polarized. You end up with a single image. And this is Strait of Gibraltar, showing the ocean surface here and the land. And because of the relatively high wind speed that is occurring, there's a wind front here. The wind causes the ocean surface to be rougher. That appears brighter in the radar image. So that's why this area is bright. The area over here, the wind is weaker. And as a result, you have more information from the ocean surface. So the bright returns here are ships. There are ship wakes here, and there's very likely an oil slick here. So part of the issue here with the copolarized image is that there are ship targets embedded in this high wind speed, but because of the strong radar return from the wind roughened ocean surface, it's hard to see those vessels. So visually it's difficult. We have automated ship detection algorithms. They struggle as well. So the way to get around that is that some of the imaging modes have the capability for dual polarization, which means we can acquire a copolarized and a cross-polarized mode at the same time. And when you look at that, there's a dramatic difference in the information content. Here's the copolarized, here's the cross-polarized. And in general, it takes multiple bounces in the target to generate a strong cross-polarized return. So for the most part, the ocean surface is, moderately flat. So you get a weak cross-polarized return, but the ship targets, the land show up extremely well. So looking at this area here, you can see, visually that there are bright targets there, which are ships. They are embedded in this high wind area here, but it's challenging to detect that visually. It's also challenging to detect that with an automated algorithm. So the nice thing about adding the polarization is that we can extract the wind speed from the data. We can get ship wakes. We can look at oil slicks. When we go over to the cross-polarized, we get better signal to clutter, better detection performance with the cross-polarized for the ship. We also have very good land-water contrast. So finally, we go down to what's called the quad-polarized mode. And in radar, the quad-polarized mode provides the most information that a radar can detect. So as the name implies, the quad-polarized, we acquire all four data channels. So the copolarized and the cross-polarized. And then one of the key information components of the quad-polarized data is called the copolarized phase difference. And in essence, what this is the timing difference from the time it takes the radar signal to leave the satellite, go to the ground, come back to the radar, and then you compare that to the same polarization state, the vertical versus the horizontal. And in general, the transmission through the atmosphere is the same, but it's the way that those polarization state interact with the target. So be it a ship, be it water, be it a forest. And there are well-known relationships between that timing difference, or in essence, the phase difference, and that can be exploited to gather more information about the target you're looking at. And this notion of phase is used in a lot of radar applications. And Bob will talk about that, the exploitation on the phase, looking at deformation. So we look at an image, it's an agricultural area just south of Vancouver. So this is the area here. This is the horizontally polarized image. So with single channel radar, that's what you get. When you go to the cross pole, because of the crops and the land surfaces there are scattering that wave in a different manner, you have a different return from the cross polarized. And then finally down to the vertical polarization. And the return from that also is a function of the type of crop or whether the field is planted or fallow. So that information, those three data channels, I haven't shown the challenge. Well, I can show the phase information in a sense, but I haven't done that. But the combination of these three data channels and the phase information, as I mentioned, gives you the most information that you can extract from a radar from a polarimetric point of view. Finishing up this by looking at the radar wavelength. So the radar wavelength depends on the particular radar. So three of the most common ones, there's an X-band radar, a C-band radar, and an L-band radar. And the typical wavelength for those in X-band is about 3 centimeters. C-band is 5.5 centimeters. L-band is about 23 centimeters. So in general, the longer the wavelength, the greater the penetration. And as soon as you add any moisture content, the penetration reduces dramatically. So if you're looking at very dry soil, X-band, 20 centimeters roughly, C-band, 40, L-band, about 1.5 meters. And the second you add any moisture, the penetration drops dramatically. So, X and C-band on the order of a couple of centimeters, L-band, just under 10 centimeters. But as soon as you get into water, the penetration is effectively zero. And so the long and short of that is that if you have something under the water, be it a submarine, be it a bridge, whatever the case may be, whether that's, 1 meter under the water, 0.5 meter, or 1,000 meters, there's no penetration by the radar whatsoever. So you have no information below the water level. Okay, so that was a brief walkthrough of to some of the fundamentals of radar. Obviously, one can go into a lot more detail on this. It's an incredibly fascinating subject to dig into and understand what things that can be done by radar. It's just really amazing. So going now and look at some offshore applications. If we look at the visual and SAR oil slick appearance, if you look at a photo, so this is a photo of an oil slick taken off the coast of Louisiana, and this was taken about 2 hours before the RADARSat 2 acquisition. So this is a classic response, a visual point of view. There's a slight change in the color, if you will, the way the light waves scatter for the presence of oil on the ocean surface. When you go to a radar, it takes very, very little oil. For example, a very thin oil like sheen, for example. And in a sense, what that oil does is that it dampens the very small scale ocean surface waves. And the act of dampening that makes the ocean surface appear smoother. And as a result, that smoothness will reduce the radar scattering, and the area of oil will appear dark in the image. So this is the area here. This is the oil slick from the radar. This is the radar, and this is the photo direction here. So this point here is this point here. So this is a long-term oil seep coming from a severed wellhead. It comes to the ocean surface, is ejected by the wind and the currents, and then spreads out. So I briefly talked about this, but why does oil appear dark in a SAR image? So the viscosity plays an important role of this, and it dampens what are called the capillary waves. And these are the small wavelength, a few centimeter wavelengths, waves that are generally on top of the ocean surface. They're driven by wind dominantly. And this scattering is termed Bragg scattering is the mechanism that occurs. So the rate of dissipation of these capillary waves is proportional to three key parameters. One is the kinematic viscosity, one is the ocean wavelength, and the other one is the boundary layer thickness. So what it boils down to is that an oil slick is particularly effective at dampening out the short capillary waves, and that results in reduced backscatter. And as a result, the area on an ocean surface that has oil on it will appear dark in the image. But not everything that's dark on the ocean surface is necessarily an oil slick. If you have rain, for example, if you have, moderately strong rain cells, the area where the rain is falling will have that same effect. And that will also cause dampening of the ocean surface. So that area will appear dark. If the rain is strong enough and typically in equatorial areas, very intense rain cells, the rain is strong enough that you're actually getting scattering from these rain cells. And that scattering is, sort of rough surface scattering. So it appears bright in the image. So this area here, this is a very intense rain cells. And these are a little bit weaker rain here. So when, if one is doing analysis, there could be oil in there, but because of the characteristic shape of rain cells, it's relatively easy to discern that this is very likely rain versus oil. You can also have the presence of low wind and also oil seeps. Now, oil seeps are, of course, oil, but if you were discriminating oil pollution from oil seeps, it's good to be able to do that. So areas of low wind. So when the wind is relatively low, the ocean surface is not roughened. So to the radar, that area will appear smooth and hence will appear dark in the image. So this area here was relatively smooth. It appears dark. And we know from this area that oil seeps are quite common, but these are some of the characteristic shapes of an oil seep. And with that, one can say, yes, we're confident that these are oil seeps, these are wind. There's also an interesting oceanographic phenomenon that's called an internal wave. So the internal waves are formed where you have a density difference within the density structure of the ocean itself. So it's not the actual waves that you see, but it's actually the convergence and divergence of the ocean currents that the waves generate. So areas where you have divergence, you're effectively stretching the ocean surface, if you will. That makes it appear smoother. And where you have convergence, you're making the ocean surface appear a little bit rougher, so it appears bright on the image. So what you end up with are these dark and light bands that are associated with internal waves. And finally, just looking at biogenic surfactants. So these can come from phytoplankton blooms, algae, and fish oils. And, whether it's, biogenetic oil in this case, or mineral oil, it has the same effect in terms of dampening the ocean surface roughness and making the radar image appear dark. So all of these are false positives. And, with time, both a combination of visual and the applications of various algorithms, one is able to discern, is this a rain cell? Is it an internal wave? Or is it an oil spill, for example? Okay, just carrying on now, just looking at an application that may be more germane to your interest. One of the areas that we do quite a bit for a number of oil companies is look for the presence of oil seeps. So just very briefly, depending on the geological structure and the formation, if there's oil and depending whether seeps occur, but over time, this geological structure will release the oil. It goes to the ocean surface. A number of droplets coalesce, and you can end up, with slick sizes of various sizes. Certain parts of the world, the Gulf of Mexico, for example, very, very prolific oil seeps, and other parts of the world where there is good, offshore oil extraction, those areas are not as prolific. So essentially, so the oil seeps come to the surface, and this is off Angola. And we imaged this. There were 3 radar acquisitions over a course of about 3 weeks or so, or 2 weeks. And these features here are the oil seeps. These are the 3 individual images. And so when these are overlaid, you can see that each one of these seeps from here, here, and here, each one of these seeps, more or less emanates from a constant area through here and here. And then with the function of the wind and the currents, they are vectored away. And that's fairly characteristic of an area where you have active seepage, that you have not known per se, but you have very discrete clusters of oil seeps. And when we looked at this, so these were from RADARSat 2, and these features here were from ERS data, which was a radar satellite that isn't functioning anymore. But these data here were collected about 10 or 12 years before the RADARSat 2 acquisition. And when you overlay them all, what you end up are these clusters, and these clusters tend to be fairly spatially coherent. They don't necessarily have a distinct temporal pattern, but over time you can look at them and look at that sort of a spatial temporal pattern. And then with this information, the oil companies will use that combined with other geophysical information to do further exploration. We have been asked a number of times to look at gas seeps, and this is extremely challenging with radar because some of the gas seeps, they're just gas and very, very difficult. Some gas seeps have a little bit of oil mixed in. Even that is extremely challenging. But this is off the, oh yes, I've got to duck out of this. Okay, here we go. These seeps are off the coast of Santa Barbara, California, where there are natural oil seeps and gas seeps. But on the ocean surface, this is the gas coming up. And from a radar perspective, there's very little difference in the ocean surface from a radar point of view, whether this was, gas or oil, which is why in general it makes it extremely challenging to do gas seeps. But in terms of looking for natural oil seeps, as I mentioned, this is a very, very straightforward application. Finally, just looking at the overall area of just oil slick detection, we also do a fair bit of work of monitoring offshore platforms. And in certain jurisdictions, there's a requirement that the platforms aren't supposed to leak any oil. And so we have a number of contracts with various oil drilling companies, and we monitor their platforms. And in the event that leaks are detected, we can provide them with that information. They can introduce some mitigation efforts. And then there's just the general area, which isn't really oil and gas per se, but the general area of bilge dumping. And both off the east and west coast of Canada and off the coast of Europe, there are very active ongoing programs with spaceborne radar to monitor shipping lanes to look for illegal bilge dumping, because fundamentally a ship is not supposed to dump bilge oil, in the coastal areas. And their principal, they're supposed to release it when they get to shore. So finishing up here with what we term nature-based solutions. So there are a number of companies looking for ways to reduce their carbon footprint. So for example, Shell Oil is aiming for net zero carbon emissions by 2050. And there's a variety of ways of doing that. But one way that, Shell and many other companies are looking at is by looking at offsetting their emissions by nature-based carbon credits. And the way that they do that is to monitor their worldwide operations and to look for any changes that were introduced in the biomass. And that's fundamentally related to forest cover and hence carbon storage. So as I just mentioned, the key input for the biomass change is the detection of classification of forest change. So we have developed a semi-automated forest change algorithm called the FAS. And for most of this, the routines in this algorithm, it's automated. But the one part that isn't is in the classification of the visual changes. So we have been doing the visual classification. It performs very well, but from a scalability point of view, it's not great. So we just completed about a year or so ago, we completed the development of a deep learning algorithm that, automates this process, to a very high degree. And we had very, very good results from that. So this isn't the deep learning algorithm here, but just showing you an example here. This is in Malaysia. So these red polygons were derived from our forest change classification. So once the data are put into the algorithm, the entire algorithm runs automatically and will automatically generate these forest change polygons. And when you look at that, these are the areas here where there have been harvesting. And, it's not, we don't expect this to be a perfect delineation. We use that to target the areas where there's been harvesting. And if need be, we can go in a little bit, do a finer demarcation. But for the most part, this did an extremely good job. Okay, so, a brief walkthrough on SAR concepts and some offshore applications. Then I'll transition over to Bob, and he will talk about land-based oil and gas applications.
Great, thanks, Gordon. Do we have any SAR basics or SAR science questions at this time? Is there any burning questions from anyone?
I think we can continue in this time.
Continue? Okay.
Yes, thanks.
All right. So what I will lead you through now are the onshore or land-based applications of the synthetic aperture radar. I'll start with the pipeline monitoring service, and that is MDA's solution that we offer to the market. And we've done a number of projects globally using this approach, and it continues to evolve and change with the different capabilities of the sensors and satellites that we launch. I should mention now, before I forget to, that we're building another satellite called CHORUS-C, which will be launched in 2 years, and it's a large radar satellite similar to RADARSat-2, and it will have a smaller satellite following it in orbit called CHORUS-X. So you can see that in the news releases from MDA, but I won't dwell on that right now. That's called continuity of mission in our business. All right, so the pipeline operators will have continuity of C-band radar and X-band radar missions. All right, so what pulls MDA towards these pipeline operators? What are their needs? If you start from the outset of a pipeline program, they're looking for specific routes through the terrain that may have minimal geohazards and potentially less movement across the slopes of an area. During operational monitoring, after the pipeline's built, there's an above ground, which isn't always the case. Most of our pipelines in Alberta and other places are buried, more like this one, I guess, in a way. But the next piece is who's operating near the pipelines, and are there any risks for third-party strike of the pipelines? Is there land use change, not only in the urban areas, but in rural settings? Oh, that's a spelling error there. Rural settings, industrial activities, mining, and forestry tend to impact the integrity or the risk factors around a pipeline. And finally, what can we provide to the companies in terms of the emergency response side of things? There's of course, in the deep sort of southeastern US, there's always a threat of the hurricanes and flooding around rivers, and what kind of impact does that have on the actual hydrology, the river erosion, the bedding, the kinds of hydrologic features that pipeline operators are very interested in. Okay, so the benefits of using satellite radar technology and these things as an asset in an integrated program would be that you can know sooner. If we set up a routine monitoring program where the satellite is actually programmed to image specific lengths or segments of pipelines regularly, then we're able to catch changes faster. We're able to see geohazards faster, and other integrity risks like encroachment will come to our attention, and we can provide alerts to the pipeline operators sooner. So surface movement is something that I'll go through in greater detail, but we can measure that at high precision with the right kind of terrain structure and vegetation cover. I'll get into the details of that. And then in that way, we can queue airborne and field surveys, which are more expensive and more risky in many cases. And the latest thing is queuing drone surveys as well. So no more. So we can do that, and we can see further, not just the pipeline right away. Some of the geospatial applications that you'll see are airborne or drone based, and what they do is they fly along the actual right of way, but the radar actually provides a full geographic extent for risks over the broader area around a pipeline. So imagine those swaths that Gordon was talking about, covering a larger area, so that if you have a failure in a like a landslide upslope in part of a hydrologic basin, then you end up detecting that potentially earlier with the radar satellite than with just airborne response along the right of way. One thing we haven't dwelled on, but you can see this in the literature, radars are all weather and image at day or night for monitoring remote and restricted areas without putting staff in harm's way. So the microwave penetrates cloud, haze, smoke, and then provides a clear image back to the satellite, okay, or capability of clear imaging. We can go backwards too. This is a bit tricky because you can't always go back, because if the satellite wasn't turned on in a specific area, you might not have the optimal beam mode, as Gordon was describing, or the optimal look direction or coverage. So that's that it is possible, and we've done many archival type projects to demonstrate the technology, but it isn't necessarily 100% slam dunk that you're going to have a really good archive to do these kinds of measurements that I'm going to describe now. So we're a leader in this area. We do have this pipeline monitoring solution that penetrates the clouds around the world, and it's possible then to integrate high resolution optical imagery into our solutions, and we do that regularly. And this is something we've been doing for over 30 years. Okay, what do they really need in terms of the pipeline operators and in terms of information? So some of the hot points that they're really keeps them up at night would be encroachment detection alerts, geohazard detection alerts, and providing reclamation and environmental conditions to support their annual regulatory reporting, and then really trying to assist in their overall integrity and damage threat reduction programs, or geohazard monitoring programs. Okay. As Gordon said, what do we see? This is a backscatter image over here. I think this is actually Vancouver again, where we don't only image Vancouver. We image the world, but here's another example of just near downtown Vancouver, where the bright buildings are, bright reflectors to the radar. The imagery is hitting the building and bouncing back. The trees are more diffuse scatterers, or vegetation. So the microwave energy hits the vegetation and kind of scatters back. Some of the energy comes back to the satellite. And then finally, there's this notion that the water reflects the radar energy away from the satellite, so it appears black. Okay. So that's a backscatter image, or an amplitude image, as we call it. So RADARSat 2 is a C-band SAR that's owned and operated by MDA. We also work with two other partners, one with an L-band SAR, which is a 25 centimeter wavelength. Remember, C-band is 5 centimeter. And then we also work with a constellation of X-band small sat SARs out of Finland called ICEYE, and they have an X-band constellation that is capable of seeing, like, say, ships or spills in small areas around the world. So it's a smaller focused mission. L-band is a little better for vegetation penetration, but there's limitations, and we understand all of those types of things. But again, they're all weather and light independent, active microwave pulses. And then there's two pieces of the radar signal that we use. One is the wave or timing difference between dates of imaging, which we call phase differences. And I'll describe that. And we use that to perform or develop something called interferometric synthetic aperture radar for measuring ground movement. Okay. So there's one piece is the phase. We use that for INSAR. And then there's the backscatter, which I just showed you, which is the amount of energy reflected back to the radar. That gives us information about encroachment and land cover change. Here's the orbital idea again. It's a polar orbiting satellite.
Bob. Sorry for interrupting you. Our system just restarted. Please give me 30 seconds to turn it on again. Sorry about that.
Okay, no problem.
Sorry, yeah.
How far did we get?
Like last 2 minutes.
Okay.
Yeah,
okay.
Sorry about
I'll
that.
Stop and no
yeah,
problem.
It is 15 seconds to restart everything. It was
okay.
Yeah, my bad. Sorry.
No problem at all. Do I need to reshare?
No, everything is good. Everything is good. We just lost our video projection. So
okay.
It is now almost almost we are board. So it is turning on. The video projectors are being turned on. And yes, go ahead, please. Sorry about that.
No problem at all. I'm just going to check with you to see what slide you see when you get it booted back up.
Okay. Yeah, I think from the last slide, yeah. No. Yes, okay. Exactly. Here. Yes. Thanks.
This one you've seen?
Yes.
It's this one.
Yep. Exactly. Thank you.
Okay.
Sorry about that.
Okay. No problem. So there's, as Gordon mentioned, there's many radar satellites on orbit. Our preferred satellite is the one that we own and operate. It's a very robust commercial satellite. It's a large satellite. It's about the size of a school bus, whereas some of these other satellites like the ICEYE Finnish constellation, there's more of them, but they're not as stable in orbit, and they're also much smaller and not as robust, let's say, in the orbital plane. We have two portions of this signal that we work with. One is the phase, or the amount of time it takes for the radar signal to be sent out from the satellite, hit the ground and come back to the satellite. That's the phase timing. And then the backscatter is actual amplitude or brightness related to the structure and texture of the terrain that it's striking. So from pipeline monitoring, we have a variety of beam modes, as you've heard from Gordon, and we tend to go with the finer resolution beam modes. So we have things like ultra fine, extra fine, and so on into this sort of standard beam mode. But these are our preferred two, right down in the lower end here, because it's a trade-off between large area of coverage and finer resolution. So here we see some wide ultrafine, 3 meter 50-kilometer swaths in Ecuador. One is where the satellite is ascending and the pipeline runs right through here, and the other one is descending. So we're able to image the length of this pipeline from two different look directions using both ascending and descending tracks of imagery. So here's the phase change analysis, interferometry, and here's the amplitude change analysis over here. This is for encroachment of vehicles like we see here, or it could be changes in the land cover like deforestation. In this case, we're looking for the deformation of the surface itself with interferometry. We always use a stack of radar images, not one or two. We always use stacks. So here's kind of the a cartoon or a video of how this works. So day one, RadarSat goes by an area and it produces a scanned image, as we've said, or an image. And then the second pass is quite a bit later. It's 24 days later to exactly the same position in orbit. It has to be well-controlled orbit and well-known orbit, and we can derive some drifting in the satellite at orbit, but it has to be very well controlled. Okay, so that's interferometry from RadarSat 2. What it gives you is time 1 and distance 1. The ground is here. With the extraction of oil, time 2 and distance 2 changes. And so this is how we use the phase shift in the imagery to produce a measurement of a few millimeters change using the SAR phase information. It's pretty spectacular technology. It is, you can search interferometry in the web and find lots of published papers around this technology. That's how it works. It's phase information that we're using. We have three types of phase derived information. One is wide area interferometry, which covers an entire oil field. We have coherent target monitoring. That's where you saw how it brightly bounces off of buildings and creates a very bright return to the radar. And then we deploy artificial corner reflectors in some areas, like you see in the lower right here, if we have issues with the ground surface decorrelating the radar signal. Okay, so three different ways. Here's what our corner reflectors look like. They're scattered all over the oil fields in Alberta, and I'll explain that to you in a few minutes, why we do that. It's a signal to noise kind of situation where we've got a noisy natural vegetation with lots of snow cover, and it's sometimes the better way to do it is with installation of corner reflectors. But you can also get some lots of information from the kind of the natural terrain using wide area interferometry. Here we have one of the largest oil fields in the United States. It's called Belridge. It's been monitored by MDA for 20 years, and it really creates this monitoring technology or technique that allows us to see subsidence as they produce the oil and try to prop up the reservoir with hot water or water flood or steam. Okay. And then some of our products, the delivery looks something like this. For a slope detection geohazard, here's the pipeline running through the hills of California. We have a measurement where the downslope is moving this way. We're detecting it with the wide area interferometry. And likewise, there's some sort of motion going on in this valley near the pipeline. But as I mentioned, you get to see a larger area with radar satellite imagery than you'd see with just flying this with a LiDAR or flying it with the air photo mission. You wouldn't know that these landslides were close and potential risks to the pipeline. You wouldn't even be able to tell if they were moving with LiDAR or air photo. Okay, so that's where it fits in. It's a little different than the other sensors. I'm going to keep going very quickly. We produce pipeline risk index maps. So we combine the interferometry, amplitude change detection, high-res optical, and other sources like, is the slope going to start moving because of heavy rainfall or snowpack changes, etc. Okay, so how do we deliver these things? We provide change monitoring reports, weekly, monthly reports, or quarterly roll-ups for geohazard detections. We can work with the customer to create with their input to create these pipeline risk index maps, and we can do highly detailed movement analysis. over certain lengths or segments of the pipelines, and then we can zoom in on certain areas with even finer resolution. We deliver it via a web platform, and we provide training and technical support to the customer as they integrate it into their normal workflow. I won't go through all the benefits. We're going to share these slide decks with you, but there's the all-weather, all-time. Optical cannot see through the clouds like the radar does, but it's great as a base mapping layer. And when you can peek through the clouds, you can supplement the radar with it. Okay. And what companies are doing as best practices for asset monitoring with radar sat. So it reduces the risk for boots on the ground. It increases your efficiency of flying other assets or field surveys. And it's a cost-efficient way to regularly see the full pipeline. So a lot of companies don't see their full pipeline networks regularly. Okay, so this is a really great way to image it regularly and then queue the other assets you have to focus in on certain areas that are problematic or potentially problematic. Typically, companies will do a proof of concept on a 250 to 500 kilometer segment of their line. Remember, these lines are thousands of miles throughout Canada and the United States. And then we can use other satellite sensors to cover things off if we want to supplement what we get with RadarSat-2. Just a couple quick case studies on pipeline monitoring. Here we see something in Wyoming where the snowpack is melting and the rains are occurring early spring in Wyoming. May, June, we start to see a little more decorrelation of the signal. Here's the pipeline running through it. It's a high pressure liquids pipeline running right through a slope, as it turns out. And finally, by June, July, things are dried up and there's not much motion, detected motion as an alert that we would provide to this company to say that this slope is potentially moving. So not much motion there by the end of the season. But overall, it provided enough information that they directionally drilled this pipeline right through the landslide so that they reduce their risk. Natural gas pipelines running across oil fields are an issue. So here we have, in a number of oil fields, we have natural gas flowing through from one operator across another operator's medium grade oil production, and really you're able to detect temporal changes in the land surface elevation, let's say, so deformation changes that might affect the pipeline integrity. Similarly, underground mining approaching a high pressure liquids line and can give the operator all sorts of problems, right? And not knowing where the underground miners are specifically, in this case, it's probably it's block and longwall mining. It's not very deep mining, so the surface tends to collapse. And so as this mining was approaching the line, they actually pulled the line out and let the miner go underneath this segment of the line so that it wouldn't destroy it. Spills and floods are issues, and we respond to those. And we also provide this kind of monitoring in very cloud-prone areas where there's a lot of human interaction with pipelines. Let's say we have a line that's running through the Niger Delta here, and there's been years and years of pipeline tapping that has been going on, and we can kind of see those changes as Gordon described. You can see the amplitude changes, and then cue other assets like optical imagery to focus in on where those tappers may be operating. So that's what I have for the pipeline side of things. Now I've got about 15 more minutes, and I'm going to focus in on what most of you may think is pretty interesting, I hope, for Alberta. Let me just hold on a second. And other oil fields around the world. Okay, are you seeing new energy infrastructure ground movement monitoring?
Yes.
Okay. Let's see if I can get it to go big. There we go. Are you seeing the full screen now?
Yes, we do.
Okay. So let's look at how interferometry is used in Alberta specifically for monitoring heavy oil production. And then I think I've got some other case studies in other parts of the world as well, if there's interest in those areas. So we'll look at heavy oil in Alberta and globally. We'll look at have a quick discussion about CCUS projects, so carbon capture and utilization storage projects, and then some notes on hydrogen fields and how will they look differently than what our normal oil fields look like, and how we can use radar sat or radar imaging to monitor those fields. So just a kind of a cartoon of what types of work do we do? Well, we provide information that allows companies to protect their assets. There's comprehensive solutions available from MDA related to the monitoring side of things. We help and work with the companies to set up optimal monitoring approaches to heavy oil production, like CSS or water flood or steam flood operations. And the objective here sometimes is to prevent well casing failures or outbreaks or breakouts of liquids or gases at surface. And of course, you know that if that type of thing happens, then operations are shut down and you lose a lot of money. So seeing something early in terms of either a subsidence or an uplift of a out of zone movement of gas or fluids is really interesting and important to these companies. And then finally, the motion as we move into this next decade, there's going to be a real focus on carbon capture and storage in Alberta and around the world. So what can we do with interferometry to support those kind of projects? Okay. And so I'll run through three different ways of monitoring. One is with the corner reflector distribution across an oil field. One is with the cyclic steam stimulation, and then the other one is wide area monitoring of a natural oil field. Okay, again, owned and operated by MDA, so we control the programming of the satellite, where it's pointing and what kind of beam modes we're using. And then we're going to focus in on this wave phase difference. It's a stack of images, like I said. We're focused on interferometry now. We're not using the fine beam mode necessarily as we do with pipeline monitoring. We can use a little bit broader beam mode in kind of, we can use spotlight, that 1 meter mode. Ultrafine here again is interesting for monitoring a lot of oil fields in Alberta. And then we can use coarser resolution depending on how large the actual carbon capture and storage program is, or how large the oil field is. Okay, we've looked at this: wide area, coherent target, and corner reflectors. Remember those things. That's how we do this. So in terms of setting up and measuring very subtle or small signals that are kind of hidden by the vegetation on top of the ground, we're trying to measure the ground and how it's related to the overburden and the reservoir at depth. So it's this kind of monitoring is used for enhanced oil recovery, support natural gas storage sites. Some fracking projects have had success with using this for cumulative frac signal detection, carbon capture use and storage. Coal bed methane is an application. And then I've got a question mark next to hydrogen production fields because we don't have any yet. But we're pretty sure that this will work depending on the depth of the production. So there's a list of benefits that you can have a look at, and it's for the key drivers are for improved production, compliance, and safety. So we want to decrease costs and increase profits. We want to make sure that the annual reporting is meeting regulatory regulations. And Yeah, we're seeing customers connect the surface information we provide to their geomechanical and reservoir models. And that leads to more effective injection production balancing. So fluids balancing, I'll show you an example of where that didn't happen very well and what we detected at surface. And provides that reporting graphical geospatial data. And it does provide it with regular monitoring, routine monitoring, can allow customers or us to detect potential damaging breakouts or subsidence or sinkholes developing on oil fields. And finally, this well casing damage is a big issue in the United States. It costs over $350K for a new well to be drilled now down in some of these areas. And I know that's not as expensive as a SAGD well, but it's pretty expensive. And there's so many wells in some of these oil fields in California. It's unbelievable. And to save some of those wells by providing interferometry is a really big cost savings for the companies. So cost-effective regular ground monitoring, long-term monitoring programs. It's a direct measure of surface uplift. It's a proven technology, this interferometry. And there it is, proven technology in a growing industry and regulatory acceptance. And the customer does not have to work with the INSAR. We work with them geospatially and connecting the data sets properly, but it's a turnkey service from MDA. Products and deliverables. Just a quick snapshot for you. Geospatial, like geotiffs, with the point locations of the corner reflectors, profiles, again, point measurements along a transect throughout a SAGD or a CSS operation. And we can be flexible with the monitoring frequency. We can monitor up to every 4 days in Alberta with one satellite. We can do daily satellite monitoring if a customer wants it, and we would just use more satellite radars. We provide GIS-ready shapefiles, an image, and technical reports. And in the case of the corner reflector measurements and the coherent target measurements off the existing buildings, we provide spreadsheets basically that companies use to ingest into their information management systems. Again, California, USA, gas storage sites, and a situation where the subsidence caused buckling of a pipeline, a natural gas pipeline, across a field. So in Alberta, it's a little trickier because we have the nice boreal forest on top of our heavy oil fields. And so we've developed over the last 20 years these corner reflectors, which if you drive out into any of the major oil company oil fields in Alberta, you'll see our corner reflectors scattered around over top of the patterns. And we'll use a combination of corner reflectors, natural targets like buildings can be used, and then we can use wide area INSAR in certain times of the year when the leaves are off the trees. So CRs are more or less subjective to noise and very reliable to millimeter per month kind of measurement. And you can see we've set this network of corner reflectors up with this particular operator to represent what's happening with the 1 kilometer long by 1 kilometer wide SAGD pattern of wells. And then we can use all the hardware at the well heads as natural, as we call them, natural targets. So a combination of those two things, we can create a surface or we can create profiles at each one of those corner reflectors on usually a monthly basis is good enough for this kind of operation. That's coherent target monitoring. We use the natural targets. And then for more aggressive steaming projects like cyclic steam stimulation I can mention this because it's published. This is a CNRL Primrose site. So monitoring that site with interferometry looks something like this at surface, and the model for net over injection looks something like this. So there's very high correlation between what they were predicting with their modeling and what actually happened at surface based on what was being the pressure distribution to surface from the reservoir, okay, or the fluids. And so, this is what a typical radar interferometry image might look like, deformation map might look like. And we can see that there's a great uplift right in this particular location, up to 25, 30 centimeters of uplift while they're steaming here and then soaking and producing throughout the area will return back to ground level. And then finally, let's say we have a wide area INSAR solution that's perfect for semi-desert kind of conditions like this, where there's high production, and it's enhanced oil recovery down in the States. In this location, it's water flood and steam around the edges of the reservoir, and this is the kind of image we get. Deformation map looks something like this, where we're actually matching it up to net voidage calculations by the company. And so they're highly correlated, well known, and monthly movements are like in that 5 millimeter per month at surface. In the California, it's a Bakersfield area there. So yeah, failed casings, 350K per casing. So if we can help them reduce the rate of subsidence in these fields, so that the fringes of the bowls are not moving rapidly, that's the winner in terms of the cost savings. So since they started to use interferometry, they save an average of $20 million in wells. So it's a huge cost, benefit over cost to them. We've also indicated, as you monitor regularly, you can detect things where somebody left a series of injectors on over the weekend, and that wasn't good because we ended up with an uplift situation within the field, which it shouldn't have been there. So we alerted the customer, and they went back out and shut that well down, shut the injectors down fine, and then kept the producers going so that you can see the deformation signal returned back to a normal type of subsidence over time. Okay. Finally, a couple comments about the use of optical. I haven't spent much time with that. We are the largest reseller of optical imagery in Canada for Maxar, and you may have seen some of the Maxar on the news recently and continually with the invasion of Ukraine. It's a Maxar image that you'll see on most times on the news. But here's what a typical red, green, blue color composite looks like in Alberta. This is recent and over a specific site in central Alberta. This is something you could get from Google Earth, but you don't actually get the bands, red, green, and blue, to do any analysis from. If you zoom in on that image, I just wanted to show you as an example the level of detail that's possible from optical satellites now. And it's unbelievable with respect to the amount of hardware information you can get from these. You can see the pipeline being constructed here, and vehicles on the pipeline. You can see that they've reclaimed this strip in here. There's different types of vegetation that you can note. But the real winner for us in our work is the band combination called near infrared, and this has been around a long time. I did environmental assessments in the 80s using airborne infrared, but what's different nowadays is these are 30 centimeter pixels now in the optical world, and you get this kind of resolution over your assets anywhere in Alberta. You see the effect of clouds, so this optical imagery does not penetrate clouds. So you got to get a clear, sunny, beautiful Alberta blue day to get this kind of imagery. But when you get it, it's spectacular. You can see, areas that need to be reseeded along this area. You can see healthy vegetation is bright red, different vegetation types based on the texture and color of the trees. And if we go back over, you can see the types of crops in the area as well. So a lot of information on the optical side. And then if you fuse that with the radar and the measurements that we can get from the radar in terms of the uplift and subsidence, slope stability, the offshore seep and spill detection, land cover land use, and remediation support. You could see that on the last optical imagery there. And it's perfect for asset monitoring, whether it's carbon capture and storage, EOR, and hopefully in the future, hydrogen project monitoring. And that's all I have for today. Appreciate your attention there, Hussein, and everyone. And we'll open the floor for questions for 15 minutes.
Thank you so much, Bob. Thank you for your presentation. Do you mind if you don't share your screen, please? This is the way we can. Yes, thanks. So, any questions? I have a couple questions for Gordon. Yeah, Gordon, do you hear me?
Yes, I do.
Sure. So, in slide number 17, there were some images from winds effects. Okay.
Yes.
I was wondering if you transform the images from time domain to frequency domain, and watch if you can find out the pattern of waves in your images. So in that way, you could eliminate all those, because wave is like a pattern. And in frequency domain, maybe we can see something regarding that artifact. Did you do something like that in your image processing, or did it work or not?
So you mean the frequency domain of the radar signal? Is that what the frequency
Yes.
domain?
Yeah. Does that work even?
Yeah, I mean, so typically for ocean waves, in the case when you detect ocean waves, they show up very well in the radar image. So we have not necessarily looked at the frequency domain to get at ocean waves because they show up extremely well.
Mm-hmm. Okay, yeah, and in another slide, you showed that you are combining three type of images, three cross polarized images,
Yes.
and you also use the phase of the images. What do you mean? What do you mean by phase?
So Bob talked about this as well. So the easiest way to think about phase is the time it takes from the radar signal to leave the satellite, travel through the atmosphere, interact with the ground, and go back to the radar. So the radar is very, very good at measuring that time.
Okay.
And so when you have different polarization, the transmission time through the atmosphere is, for the most part, independent of the polarization state of the radar. But where the differences come in is how that radar wave scatters. So there are some well-known relationships between common scattering mechanisms, and the three most common are called surface, double bounce, and volume scattering.
Oh, yeah.
And so for those three key radar scattering mechanisms, there is a very good understanding of the phase difference between horizontal and vertical polarization. In terms of the cross polarization, there's very little in the way of usable phase information. So it's typically the key phase information is the phase difference between the copolarized HH and the vertical polarized VV.
Okay, so next question for you is, okay, so do you reconstruct that you are reconstructing your responses coming back from the satellites to provide to generate images, right?
Yes.
Yes. What kind of reconstruction are you using? Can you describe just
Well, that's not necessarily my area of expertise.
Okay.
But it goes down to SAR signal processing.
Okay, yeah.
And so the radar waves come back to the radar. And then actually MDA is a world leader in the processing of the SAR data. So there are different signal processing techniques using, cross correlation, autocorrelation, a number of other signal processing techniques. And those techniques are used to go from what is called the raw radar image and to process that into, an image that looks like something.
Yes. Yeah. Okay. Yeah. And okay, so the responses are sensitive to viscosity, right?
Sensitive to what did you say?
Viscosity, like viscosity of oil, water, and this way you can find out the oil in the surface of the water. You can find pollutions, right? Because of the viscosity.
Yeah. So
how about density? Is it sensitive to density as well?
The density of the oil?
Yeah, the density of materials, generally speaking. Like the differences between soil and like rocks.
Oh, okay, yeah. Yeah, so the more for a given, like if you think of a rock or forest cover, the denser that is, that reduces the penetration. So I mean, radar does not penetrate rock, but if you had, a very dry sort of sand, if you will, under those circumstances, you can get, radar penetration sometimes on the order of a meter or more. And it has to be very dry. If you change that and it becomes solid rock, then the radar wave scatters from the rock and doesn't go through the rock. If you look at a crop canopy or a forest canopy, if a very dense, thick forest canopy, the radar wave depends on the wavelength, but a radar wave in general will not penetrate that very much. But a sparse crop canopy, sparse forest canopy, you will get more radar penetration.
Okay, yeah, that makes sense. Thank you. And the last question is how that FAS algorithm, the semi-automatic algorithm, helps you in what regard? It is just providing some pre-processing for the human expert, and then what does that work in your interpretations?
So essentially, what it's doing, if you look at an area of a forest that's been harvested, it will typically appear dark in an image.
Yeah.
And there may be other things that look like that as well. So what the algorithm does is to go in and, not so much just look for a dark area, but it's also looking for other parameters. And it will go through the image, and it's working on, at least two images. So it's taking one image and comparing it to another, and it's going through, it's applying various techniques to filter the data and to look for those areas, those dark areas. And so then the algorithm will detect those dark areas, and it will do an automatic delineation of the dark areas. So what we end up with, we have an image, and we have areas that we believe are related to forest change. And that's the component of that overall process that's visual at the moment. So people will go through and they will visually look at those areas and compare it to maybe optical in their experience and say, is this a forest related change? Is it water, or is it something else? So that was the whole issue for us developing a deep learning algorithm.
Yeah.
That visual classification is time consuming, but the deep learning algorithm is very fast, and we had very, very good results with that.
Yeah. And sorry, but it is my last question, I promise. So in the Indonesia case that you showed us about the progression of forests and things, is the algorithm able to, because those two images were exactly the same, the position, the length, the size of the images, they were exactly the same. Is the algorithm able to work with those images that they are not the same size? So I was wondering if the algorithm is able to find some features and then resize the images itself by itself. The algorithm does that, and then process the image. Or no, the input images should be exactly the same, and then after that, the algorithm would work on finding the dark and bright areas in that regard.
Yeah. So one of the key requirements for change detection with radar is that you have to have the same image. You have, it's not so much the same image. You have to image the area you're looking at with the same radar imaging geometry. Because what it boils down to is that if you were to change the radar imaging geometry, there could be a change related to the radar imaging geometry and not the change on the ground. So when we do change detection, we exploit one of the capabilities of the satellite is that it's every 24 days. It will come back to exactly the same position in space, within reason. It could be out by 100 meters, 200 meters.
Yeah.
Then we image the area, we apply the change detection algorithm, and then the changes we detect, we are very confident that those changes are related to changes on the ground and not changes due to the satellite. And if we were to, use different imaging geometry, you could easily have changes that are solely related to the imaging geometry. And that's a common attribute of radar, is that you have to image using the same imaging geometry.
Yeah, that makes sense. Yep. Awesome. Thank you so much for your presentation. Thank you, Bob. Thank you for your time. I really appreciate your time and the presentation, the lecture. So I think this is the end of our seminar. And this is it. Thank you.
Thank you.
Yep.
Thanks very much. It was really enjoyable, and thanks for your questions. Very good questions.
Thank you so much for your time. Yeah.
All right. Thanks to everyone for your time to listen in, and good luck with all your studies, and work at the U of A.
Sure. Have a nice
All right.
Have a good day. Yeah.
All right. Cheers. Bye-bye.
Bye-bye. Bye-bye.